Okay, I'm starting this from the beginning, and there's only 39 slides on this, but I will tell you a quick warning is that I probably, at least probably 20% of the final exam last semester actually came from this set of slides. So these slides are relatively important in terms of this is the general background, and it's easy for me to steal questions from them. I'm going to probably do things a little differently, and I'm going to probably have a midterm exam that's a real midterm exam in class. I haven't done that, but you know, I've been kind of scolded for being a little too relaxed on some of that stuff. So I'm going to have a midterm exam. So you would probably see a good portion of the midterm exam come from this set of slides. Maybe even half of the midterm might even come from this set of slides. So it's an important set of slides, even though there's only 39. I'm going to expand on that there. And there's more slides that back this up that gives more detail on these. This is kind of the introduction, but a lot of the exam questions I asked last semester and in previous semesters have been kind of the general background, you know, what is a twisted joint, what is a pivotal joint, you know, draw a picture. And those all are in this set of slides. So, you know, they're posted. I don't have a textbook per se for this class study that there. I'm just kind of doing it off that there. And one of the reasons I don't have a textbook, to be honest, is nobody reads it anyway. That there, you know, if it's a paper textbook you had to buy, nobody would buy it because it would cost. Phone out, jabbing into me. These phones keep getting bigger, and I keep getting bigger, so the phones get tighter in my pocket. That there. So I see all the young ladies that walk around with them in their back pocket, and that there. But guys, I don't see. You don't carry your phones in your back pocket, do you? Usually, it's in your front pocket. It's the ladies that I see them carrying them in their jean pocket in the back. I would always sit down and break a phone. That there. So, all right, let me just kind of get going here. And as I said, it's only 39 slides. I may actually get through it, and then we'll call that a week, and then we'll get into more detail next week. I don't think we have any holidays or anything next week, and inshallah, I'll be healthy, although this weekend I'm taking my sister to... Okay, let me try this once more. This thing's going to nag me. I don't know why it's supposed to be one password, and I just changed it right there. Yeah, let me just, okay. I'm just going to ignore that there. So let me just kind of jump in. I'm recording. Okay, this is actually chapter 1 out of a book that, Introduction to Industrial Robots and Automation. It's a fairly in-depth book. I didn't specify it, although I'll probably use different things from that book. I might put it online if I can find a full PDF version of it, but it'll be on the VLE right there. But there. Upon completion of this chapter and these slides, and I went through that there. The main thing is, again, I don't think I can write on this here. Oh, actually, the old projectors I can. It's the newer projectors that my pen doesn't work. So this room it works. But we're going to kind of go through the definition. What is that there? We'll talk about this advantages and disadvantages. One of the exam questions I've asked in the past has been, that there is what's the effect of automating a particular factory? That there I'll give a little bit more detail. You're the plant manager, and you've got upon doing some research, you've looked at a particular operation. You've determined that you can use a robot to do this, and in doing so, you'll eliminate 20 people. That you'll pay so many hundreds of thousands or millions of ringgits for the robot. How much is your payoff? that there, this is the type of test question that may show up that there, and is this a good idea? And then of course you have to, there may be more detail in this there, but it's one of those types of questions, and I didn't ask quite this much detail, but I probably will this semester, where I want you to be able to think about what effects does that have. You've got 20 people you're going to make redundant in your plant, and the description might discuss the fact that that you have other jobs in the plant that they can go to, which is a good thing. Then you can not hire 20 people. Or if your particular plant hires a lot of foreign workers, you can send 20 people back. Or if the workers you're going to make redundant are, people from overseas, then of course you don't mind making them redundant. But if these are well-paying jobs in a plant that are hiring Malaysians, then of course, letting 20 people go, it does have an effect. So, and we'll talk a little bit more in detail of that later in the class. But these are kind of one of the things you want to think about when you look at automation and robotics, is that anytime you deal with automation and robotics, there's advantages and disadvantages right there. So we're going to talk about, the author of this book only concentrates pretty much on the advantages. Obviously, there's some disadvantages, and the disadvantages quite often are social economical disadvantages and not necessarily engineering disadvantages. We'll talk, this particular chapter lists 6 types of robot automation. It explains robot automation. I'll be bringing some videos of showing some robots working. We do have one robot on the 4th floor, I think, in this building, industrial robot. Unfortunately, it's Rozak. That's a term everybody knows, right? It does not work that there, but at least you can see the size and that there. You will be doing some labs with some smaller robots that you'll be writing some MATLAB code in order to control the arms, pick things up out there. So, but this is the learning outcome out there. And again, this just repeats the same thing. Okay, this is the definition that there. A robot is a machine that can be programmed to perform a variety of jobs. So robots can go from very simple to complex. I can give some examples of some relatively simple robots. One of my early jobs, I don't know if I talked about it in this class or not, was I worked in a factory. It was my shortest job I ever had. I only worked there 4 hours before I got bored to death. I was going to probably bring in an assault rifle and start shooting my coworkers, which is not an uncommon thing in the U.S. It doesn't happen very often here, but it does happen once in a while in the U.S. And my job was basically to sit on a stool and pick up a magnet from a table or a piece of, it wasn't a magnet at that point, it wasn't magnetized yet, pick it up and then put it on a loudspeaker as it went by. We made speakers for cars and stereo systems out there. And it was a hand operation. Somebody would bring a big push cart full of magnets out there. The assembly line would walk by, and I would pick up that magnet and put it on that cone. Pick up the next magnet and put it on that cone. The next magnet, put that on that cone. And that was my job. I was 17 years old, still in high school, and I was working at night part-time, just simply to, for different reasons. So I had this particular factory job that there. And again, as I said, it was the most boring job I ever had. So a very simple robot could probably replace me, right? Yes. And is this a job that I care that disappears? I sure didn't want to do it. And I've had some really different jobs over the years. One of my jobs when I was, about a year or so later, I had a job where I drove a machine into a chicken house and picked up all the chicken manure from underneath the cages and dumped it into a tractor and then spread the manure over the field. And you talk about a crappy job. I normally use a different word, but it was a pretty smelly, nasty job. And I did that job for 6 months to a year. I mean, I enjoyed that job. You know, and that was definitely, but the magnet job I couldn't do. That there. It was just too boring. But the cleaning the chicken manure out of the chicken house didn't bother me so much. Now, there's other parts of the job. You know, we moved chickens from one chicken house to another, but it was a poultry farm. You know, it was an operation that there. So there, but I'm sure that they don't have people manually, scooping up chicken manure anymore and spreading over the fields. It's probably been automated because those are the kinds of jobs that you really want robots to do, right? But a robot is a machine that can be programmed to perform a variety of tasks. So the simplest robot machine that I've seen, it's actually not a simple machine, but the iRobot that does the vacuuming in your house. I mean, sorry guys, you probably never touch a vacuum cleaner, but the ladies I know will pick up a vacuum cleaner and vacuum your house, right? So it's nice to have a little robot that goes around and does that for you. It's actually a very complex machine, these iRobots, because they do the mapping of the floor and keep track of that there. So, but they can range from very simple to highly complex. These are the 3 laws of robots. I hate to say it, but they've already been violated. And I was born and raised in the U.S. I spent 4 years active military, another 5 years reserve military, so I'm fully aware of what the U.S. military does. I'm not a fan of the U.S. military, but the number 1 rule is a robot may not injure a human being through inaction while a human being. Of course, obviously, that's been superseded with military drones. The military drone is basically a flying robot that, you can buy them that are remote control with cameras and spy on your neighbors or whatever So ladies, beware, don't be walking around your compounds with, skimpy clothes because, the guys in the neighborhoods might be flying drones around spying on people But, I mean, the military was the first user of drones. Although satellites actually do a pretty good job of spying If you ever look at Google Maps, has anybody ever looked at Google Maps and looked at the images? Those are pretty clear images of your house. And of course, Google has a project. I don't know how well it does in Malaysia, but they actually drive cars through neighborhoods, and you can actually get a pretty good image of your house, the front of your house from the street. I was showing my sister the other day the house that we grew up in St. Paul, and you can actually say, oh, they painted it. used to be blue and now it's gray type thing. You could actually see the house where I grew up up in St. Paul. So again, but Rule 1, and you'll be asked to recite that there. So this is one of those things I'm going to circle right there, is what are the 3 rules of robotics. Well, number 1 is may not injure a human being or through inaction allow a human being to come to harm. Now that's an important rule when you look at self-driving cars, for example, right there. Is that the cars, if you have a robot driving a vehicle or a truck or a train, if it follows the rules of robots, it's got to keep that driver safe, and it can't hit pedestrians. Pedestrians are not targets for robots. So robots must obey the orders given to it by human beings, except for when such orders conflict with their. And again, these rules have been violated when you look at military-type robots, and that's a huge controversy within the military and robotic world out there, but it is one of those cases. Robots must do what they're told. Now, of course, we're looking at artificial intelligence. The field of artificial intelligence means that we're trying to give machines the ability to think and make decisions. And what happens if a robot makes a decision that's contrary to what the human masters wanted to make? Do you have a way to override that? And these are all philosophical questions, not so much what we're going to get into the course, but I'm on my soapbox. I'll go ahead and talk a little bit about that. And then robot must protect its own existence. In other words, robots don't self-destruct. Now, there are, again, exceptions. If you have a robot that goes into a building where there's a fire looking for survivors with a camera, and you're controlling it remote control. This is a little remote control car that's really essentially a robot type device it's going out there. And these things can be smart. In other words, you may not have a control. The robot may go through the building on its own and using artificial intelligence, look for possible survivors in the building out there. And obviously that building or that robot may put itself in harm's way. It may go into an area where it's going to get burned up or something's going to fall on it. But robots are, in most people's minds, cheaper than human lives, right there. So when we look at robots in the area of military / search and rescue and first responders, do you use the term first responder here? That usually means police, fire, and ambulance drivers. If there's an accident, they're the first ones supposed to be on the scene. They call it in American British English, they refer to them as first responders. Some of those will use robots in terms of searches so some of those robots. So these 3 laws of robotics right there, they could find their way on a final exam and right there. And it's important that you know them. They're the ethical rules that we're supposed to follow when we deal with robots. Now, as I said, there's already exceptions to those rules, and that's created a huge controversy in many circles right there, where it's below our pay grade to argue those. We're just going to accept the 3 rules that we're supposed to follow that there. And I know that I've watched the documentaries of people that work for the Air Force that operated drones that have really, really come out against them and that there. But the first one is the robot is not supposed to injure or kill people. That's obvious. You shouldn't be designing killing robots. Unfortunately, people have already done it. But we won't get into that. Robots must do what they're told, right there, and a robot should protect itself in some ways, except for when it conflicts with 1 and 2. You notice that these each have the word accept right here, and again, as long as. So in other words, these 3 laws of robotics, number 1 is absolute, robots shouldn't kill or injure people. 2 is it should do what it's told, except for if it's told to kill somebody. So, and 3, it must protect its own existence, except for if it's going to violate 1 or 2. Now, that's kind of an interesting one, is we can deliberately put a robot in harm's way in the case of, like I said, a building that's on fire, a robot that's supposed to look for explosives in the case of So those are kind of an interesting scenario when we look at robots. Most robots, these are not issues. When we look at industrial robots, these are not issues. These only become issues when we're dealing with search and rescue type robots, when we look at putting the robot in harm's way, or military applications. I'm a little bit sensitive to that because I did work in the military complex for a number of years when I first finished college. I worked for a company called Magnavox, so we did build some, we weren't so much weapons systems, we were more electronic warfare, digital signal processing. We were tracking submarines. We weren't building guns per se or anything like that. So, okay. These are the 5 parts of almost every robot. Again, as I said, this is an easy section that they're the controller, the manipulator, the actuator, the end effectors, and the sensors. These are 5 terms you need to probably put to memory, know what they are, right there. I won't talk so much of this slide because I think they're covered. Yeah, that's it. So, okay. The controller is the brain. It's usually a CPU or computer. In the human being, it's a brain. Now, if the brain malfunctions, of course, the robot malfunctions. I'll look at myself as an example. We've got the human brain. Mine's broken. I've got defects in my brain. I had a stroke. A stroke is parts of your brain are killed off right there. So if you look at my MRI, you will see 2 sections of my brain where there was a blood clot and oxygen didn't get to that part of the brain. Right there. And I spent almost about 3 or 4 months in, about 2 months in a wheelchair and about another 2 or 3 months using crutches a cane and a walker. I lost the ability to walk and I lost the ability to use my right hand, right there. So I mean that part of the brain is gone, and part of the right side of my brain, and the brain flips over. The right side controls the left side, and the left side controls the right side. I don't know, most people don't realize that, but they cross that there. But the brain is the controller for the human body, right there. And just like the human body, if your CPU malfunctions, right there, the human brain is actually a wonderful thing. Allah has blessed us with brains that will rewire themselves and they call it neuroplasticity, which basically the brain reprograms itself. As a result, even though the part of the brain that controls my right leg and my right arm is broken, it's gone. I mean, it's never going to come back. Brain cells don't regenerate, and they don't. If you cut your skin, it will grow over, but the brain doesn't. So if I was to pull up my MRI, you can see 2 big white spots where the brain, those cells are gone, and they'll be there 10 years from now. But fortunately, other parts of my brain will take over. Unfortunately, that's what causes the stroke fatigue, because my brain shuts down for a few hours where I have to sleep, and it does its rewiring while I'm asleep. Ooh, right there. So it's kind of like taking an elevator offline so you can fix it, right? So that's what my brain does. But any robot has got to have some kind of control, right there. So I talk about myself with the stroke and the fact that my brain is the microcontroller for the human body and controls the arms, and my hand is still numb and not working 100%. As you can well see, I can use my right hand. 3 months after the stroke, I couldn't put a pin in this hand; it'd fall out. I'd do that. That's it. So but again, the controller so our controllers are important for the robotic labs. We're going to be using the controllers. We're going to be using as our computers in the lab. I'll bring one of them down and do a demo. It plugs in the USB port, and that's there. But there's actually a Arduino microcontroller in the robots that actually control the actual motors that go on. So the controller, it doesn't have to be a computer, but it's almost always today some type of computer chip, right there. Microprocessor, microcontroller, computer. The manipulator, that's the arm, right there. Now, I have trouble with my arm, shoulder, but of course my problem is not the arm. My arm works fine. The muscles are in good shape. and I go to the hospital and they make me exercise the arm. But in my case, the controller's broken. But the robotic arm comes in all shapes and sizes. The arms that we're going to see are relatively small. Our robots are about this big. I mean, they're about, I'd say about half a meter by half a meter size or something like that. But the arm is what positions. When we look at the human arm, it's got a shoulder, it's got an elbow, and it's got a wrist. Those are the three major joints in the human hand. Robots have the same type of thing in some cases. Some cases they don't. If you look at the iRobot, for example, it doesn't have any arms or anything that goes around. It's just got wheels. It moves around out there. And then it's got a vacuum cleaner and a little brush thing that spins around. It's a typical vacuum cleaner. I call it the iRobot. That's a brand name out there, but it's robotic vacuum cleaner right there. Cars, of course, don't have arms. Robotic cars, self-driving cars. They have steering. They have wheels and they have things to steer. They have brakes, but they don't have arms to pick up things. But in the U.S., they have trash trucks that have got giant arms that reach down and pick up trash cans and dump them into the back of the trash can. You don't have 5 people sitting on the back of the truck going around grabbing everybody's trash and dumping the cans in. In my neighborhood, they don't even pick up the cans. They open up the cans and grab the bags. So if you have trash outside of a bag, they won't pick it up. That's there. But, in my neighborhood in the U.S., the truck would drive down the street. It would have one person in the truck, and an arm would reach down with a giant hand, pick up the trash can, dump it in the back of the trash can, and put the trash can back. Right there. So you didn't have to use bags. You just throw things in there, and it would just get thrown into the back of the trash can. But the arm is what reaches out to pick it up. So the manipulator is like the human arm. Many resemble that. They have shoulder, elbow, wrist, even fingers. Now the fingers I don't consider part of the manipulator. The fingers are a little bit different. They're part of that end effector right there. So the simple robot we'll use the term degrees of freedom. Degrees of freedom are the ways that the robot can move. The robots that we will use in the lab, they have 5 degrees of freedom. They have 5 motors. They can pivot this way, right there. They can go up and down. They have an elbow. They have a wrist. They have the thing that turns. Then they have a gripper. So there's actually 4 degrees of freedom plus the actuator right there. So again, that's how much movement. The human body has many, many more. If you look at the human arm, the shoulder, of course, is 1 degree of freedom. And it can rotate, it can go up and down. The elbow also, but the elbow can only go one direction. If you try doing twisting the elbow, it'll go within reason, but then it springs and breaks, right? Same thing with the wrist. The wrist has got 1 degree of freedom and a little bit of a turning. So it's got essentially 2 degrees of freedom right there. Fingers, of course, really each joint in the finger has got so many. So if you look at the human hand, it's probably the most complex of that there. Which incidentally, that's one of the reasons why, as a stroke sufferer, the hand is the last one to recover because it has the most nerve signals from the brain to control it. So the ability to use my hand was the last thing I got in terms of mobility. I still don't have sensation. I'm still numb. I mean, still got that there, and I still get tired easy. But the hand was by far the last thing that I got. I could walk before I could pick up things. That there. So, but the manipulator is the arm. That's the easiest way to remember it. And this kind of shows, again, here's the arm right there. And then they're showing course, the wrist that's there. This is somewhat similar to our robots right there. We've got the movement that goes this way, right there, sweep. We've got the shoulder that goes up and down. We've got one elbow. We've got something that pitches the wrist that's there. Then we've got something that turns this way, like this. We don't have this yaw thing that's there. Then we've got the grip right there. The actuator is used out there. Now the actuator is actually the muscles. So when we look at the manipulator, it's the arm, but something's got to move the arm, right? In the case of the human being, we've got muscles that contract. We have a muscle that when I put my arm out straight, it stretches my bicep. When I bring my arm this way, my bicep shrinks. The muscles contract right there. And if you're a bodybuilder, guys like to show off their big muscles. Trust me, I'm 60 years old. I don't have big muscles to show off. That there. I used to lift weights, and I had big arms at one time, but those days passed about 15 years ago when I got in my mid-40s. I mean, there are 60-year-old bodybuilders. I'm just not one of them. So that's right. I've aged gradually. But the actuator is the mechanism used. There's 3 or 4 different types that we'll talk about. Pneumatic and hydraulic are similar to each other, right there. And there's both the pneumatic cylinders that usually move linear, that there, or rotary that turn, right there. So the 3 key ones that we have is pneumatic, hydraulic, and electric, really. Now, an example of a pneumatic is an air wrench. The guys are probably more familiar with these than the gals. But if you go to a garage and they take your tires off, you see them bringing that wrench. It's got an air hose attached to it, right there. You've got air pressure that will turn the wrench, right there. You don't have to sit there, or twist the tire iron out there. There's the air. I used to work at factories, where we had pneumatic presses, where air would open and close various things, and we had air hoses that went through the plant to provide air pressure, right there. So air pressure is a very common one used in industrial robots for small motors. Hydraulics is oil. An hydraulic cylinder is, for example, your power brakes or your power steering on your car. Up there. Most of you that drive automobiles today, I assume everybody in this class probably drove an automobile, right? Or at least looked at them. Back in my day, when the dinosaurs walked the earth, a lot of the cars had manual steering, where if you wanted to turn the wheel, you provided the muscle to turn the wheel, right there. And if the car was stopped, the wheel was very hard to turn, especially for a small person or that there. So they invented something called power steering, which has a hydraulic pump that when you turn the wheel, it puts oil in one side of the cylinder in order to move the tires to turn the car. So there's something called power steering fluid. And again, I'm picking on the guys know more about cars, but you know what I mean by power steering fluid, right? It's a heavy oil. It's an oil. It's different than engine oil, but it's a very similar product. And the goal of the engine of hydraulic of the transmission, or not transmission fluid, that's actually an oil for lubrication, although there are some but power steering fluid and brake fluid, but power steering fluid is to provide the oil for the hydraulic cylinders to turn the car. That's a type of hydraulic actuator. Another type is if you pull into a garage and they want to lift your car up on a hoist in order to look at the engine, they'll push a little button and the car will go up right there. There's a hoist. And they use oil in order to push the car up. That the air is a little too thin. Now, if you have the little hand pump that you pump up, that usually uses air pressure to pump. But these are all hydraulic cylinders or pneumatic. Hydraulic and pneumatics work very similar to each other, and we'll look at the inner workings of that. Motors, of course, are different, and you've studied enough on motors in your other courses. We'll talk about a couple motors. In particular, we'll talk about the servo motor and the stepper motors. But there's three basic drives types of drive: pneumatic, hydraulic, and electric. So those are the three terms that you probably, when we look at actuators, what are our types of actuators? We have different types of actuators. Some are linear actuators, some are rotational actuators, some are twisting actuators. Those are later on in the slides. So the robot's position also depends on the combination of these out there. So where we're going to place the robot arm is actually a function of our actuators acting on our arm right there. So we've got our manipulator, what we're moving right there, and the actuator is what's moving right there. So the robot has, then the cam. And this is just a cam, that's not a very good picture right there. The end effector, this is the important thing. This is what actually does our work. It's the gripper. It's what grabs whatever we're working on. It can be a vacuum pump. If you go to say, Intel up in Penang, where they make ICs, or even Texas Instruments there in Carmont, they've got these little vacuum pumps that pick up ICs, because you don't want to pick it up with anything electrical. Metal, because you know any kind of electric shock can blow up, can burn up the chip. So they pick up the ICs with a little vacuum pump out there. So you can have hooks, you can have scoops. If you want to, for example, tow somebody's car, the old way used to be you took a hook and you hooked onto the front of their car and picked up the front of the car and just drove it down the road, right? Or used to be the back end, you know, when I was growing up, because that's where the transmission and the emergency brake was. So you can always pick up the back end and just pull the car behind. Now they put it up on a bed, but you can have scoops. You know, if you look at, for example, a piece of construction equipment that digs holes, right there, they have what they call a scoop shovel for picking up this way, or a backhoe that picks up this way. Those are scoops. Now, notice when I talk about these, these manipulators and these end actuators and that I'm going outside robotics, and I'm talking about construction equipment and machines in general. Because robots use the same technology as construction equipment or industrial machinery. The only difference between a robot and a piece of construction equipment is the piece of construction equipment that digs holes, you know, the backhoe or the scoop shovel, has for its controller a human being in the loop. You know, a robot would just simply have a microcomputer that would actually control that. So the real difference between a piece of industrial equipment or a construction equipment or a vehicle or an aircraft and a robot is just what's controlling it right there. So everything you've talked about in terms of designing machinery or equipment and everything else carries over. Now, robotics is one of these courses that also blends in mechanical engineering, physics, electrical engineering, and computer engineering. It's a multidisciplinary area when we look at robotics. And philosophy and ethics is becoming, it's a huge part of robotic discussions. Companies are building robots because you look at, again, I mentioned the military that they're, but you also look at the ethical aspects of putting in artificial intelligence and psychology. How do the robots think in comparison to humans? Do robots think with a logic that's like humans? And that's one of the goals out there. So again, but the end effector is what actually does the work. That's why I say the fingers are like the end effector. That's like the gripper. When I pick up this mouse, it's my fingers that's doing the work. That's actually picking it up. My arm right here is how I get it into position. My muscles, as puny as they are today, get my hand in the right position in order to squeeze my fingers to pick it up. My brain tells my hand how to do that. That's there. So that's the end effector right there. So now we have our last part right there. And I'm going to keep on going. I don't know where I'm on slide. But the sensor provides feedback to the control systems to get the robots out there. So now in my case, I've got my eyes that tell me when my hand is on this mouse right there. Now, part of my sensors are gone right there. I don't have any feeling in my thumb and forefinger. So, so when I pick this up, I literally have to look at it. I have to see it. I can't, most of you probably can put your hand down there and pick this up and not have any problems with that there, but I have some sensory issues with that there. But there's 4 types of sensors right there. You'll need to know the 4 sensors, and you also need to give me examples where they're used. Now, one of the places where I take off a lot of points on the final exam is I'll say, give me, explain what a position sensor is, what it does. You give me an example where it's used. When I ask that question, is a position sensor might be, to determine the location of the arm or the location of a particular object right there. A position sensor might be, for example, your GPS coordinates for your car, where your car is at. The range sensor is how far you are from a particular object. So example of that, and there's this game I used to play it back many years ago, where you hit a little white ball and you go around and you chase it and then you hit it again, and then you try to put it in a hole, right? They call it golf right there. And people will use position sensors to see how far the hole is from where they're at in order to know which club to use. Other position sensors or range sensors might be to see how far that wall is from here to determine how much paint I need to paint between that. The range tells you how far you are for something. Velocity tells you how fast you're moving. An example of the velocity sensor is your speedometer on your car, right there. But that there, and proximities tell you whether or not you're close, right there. Proximity sensors are used a lot in, say, for example, manufacturing operations. A bag will come down the assembly line, and as soon as the bag is in position of proximity sensor will sense that, and the assembly line will stop, and a valve would open and fill the bag up with material. Then once the bag is full, it will move on and seal the bag, and then the next bag would go on. So proximity sensors are used a great deal in the industrial world, manufacturing, right there. But they basically tell how close something is right there. So range sensors tell you how far. Proximity sensors are usually yes or no. Is it there or is it not there? So where a range sensor tells how far you are from something. So range sensors tend to be a little bit more complex than proximity sensors. A position sensor will just tell you where you are in relationship to something. Now, a position sensor might just tell me an angle where my arm is, right there. So, and these sensors can be optical, they can be electrical, they can be ultrasonic, they can be visual. There's all types of ways that these sensors operate. The human brain, in the human body, we talk 5 senses, right? Taste, touch, feel, hearing, and sight, right? Those are the primary 5 senses. Now, other people talk about there's other senses that we don't talk about. Those are the 5 senses, right there. But those are the ones we process as humans. When we deal with robotics, we'll get other types of sensors, right there. Power sources, I've already talked about that. That's the hydraulic drive, electric drive, pneumatic drive. The hydraulic and pneumatics are usually pumps. So they're usually electric pumps that provide air pressure or hydraulic pressure, right there. So almost all of the source for almost all robotic is usually electricity of some form. The exception would be, for example, a vehicle that may have a gasoline or petrol or diesel engine that would drive. That's there. But when you're looking at industrials, they're almost always electric motors that generate the hydraulic pressure for a plant or pneumatic pressure. So, again, I'm just going to keep going out there. I'm good. Like I said, we missed one day, so I'm a little behind. But when I get tired, I'm going to quit. So we're not quite an hour yet. I don't know where we at. Disregard. Let me just yell. Oh, we've only talked 45 minutes. I can keep on going right there. Okay. Yeah, I guess that's going to keep that there. Let me minimize that there. So hydraulics are usually very fast. They're usually, the main thing when we look at hydraulics is that they're generally for heavy uses. So if we want to, for example, move a car down an assembly line, you probably don't want to use air pressure for that. That's not really powerful enough. You usually use some kind of hydraulic, or in the case of most assembly lines, they're using electric. That's there. But if you want to, for example, pick a car up in order to get underneath it and work on the brakes, in other words, to lift the car up, you're going to want to use something like a hydraulic right there. If you want to, for example, if you're wanting to pick up an engine from it, that there, and place it into the car chassis as part of the assembly process, you're probably going to have an hydraulic pick up that engine block. That engine block's heavy. That's there. Back when cars were made in the dark ages, when I remember seeing assembly lines that made cars, we used they used chains, and people pulled up the engine, brought it over, and then lowered it down and placed it inside the car chassis. Nowadays, a robotic arm picks up the engine, places it in the car chassis, and a couple other robot arms come and bolt it to the engine mounts. Right there, it's completely done by hand. And believe me, having been in some car factories, I never worked in a car factory. I worked for a company that made brake shoes and clutch faces for cars, but I never worked in a car factory. But I taught courses for General Motors where they make trucks. So I've been in the plant, and I've seen enough car plants and the robotics that's there. But they're going to use hydraulics for the heavy duty stuff in an automated plant. I've never been in the proton plant there in Shah Alam. I've drove by it. that there. But I'm sure that the engine assembly where they put the engines in the car and then drop the transmissions, those are going to be hydraulic robotic actuators right there. So often used in expressive environments. I don't even know what they mean by that. I'll skip that particular slide. Hydraulics are big. That they're, they tend to be heavy, fairly large hoses. And believe me, I've been in enough shop floors that have had hydraulic leaks all over the floor, and you can slip and break your neck if you're not real careful in some of those places that there. But hydraulics have some huge advantages for heavy duty type industrial applications. You're not going to find them in your little iRobot to vacuum your floor right there. But you're going to find them in a lot of the industrial applications. And again, you got to remember that manufacturing is still a huge part of the Malaysian economy. So some of you will probably work in manufacturing environments and see some of these robots with the hydraulic. Electric drive, they're a little slower than the hydraulic. They take a little bit of time to get up to speed. If you look at, for example, even an electric scooter or car, you can't go from 0 to 60 very quickly or 0 to 100 kilometers an hour very quickly. My little gas engine on my Vespa it's a little bit more responsive, and it's only 150 cc, and it's got a lot of weight to carry with me on that there. My brother-in-law, who has a 1400 cc Suzuki, wonders how my Vespa can carry me, because he's a thin guy, about 15 years younger than I am, and he's got 1400 cc, and I've got 150. Of course, I don't race them up and down the north-south highway. But again, electric drives, but they're getting better. I mean, that's why we're seeing electric vehicles becoming much more of a mainstay in today's economy. You're going to see, I think UK is wanting 50% of their new vehicles to be all electric by the year 2020. India, believe it or not, has a huge drive for electric vehicles. I haven't heard much out of Malaysia with electric vehicles. Malaysia, they had to move toward the natural gas vehicles at one point for taxis. I haven't seen the electric vehicle. But electric is actually getting to be up there. The best thing about electrical is that it's very accurate and very repeatable. Right there. Electric motors, we can get very precise speeds. We can get very precise positions there. So for a lot of really tight robotic type operations where we want to, for example, do microelectronics and do a IC etching, obviously you're going to do something with electrical motors drive. Your end actuator might be pneumatic in those cases, but all the controls is going to be electrical. There. Stepper motors give us open loop control. We'll talk a little bit about stepper motors. They're very, we can move them a set number of degrees by providing so many steps. Every now and then we have to reset them back so they know exactly where they are, because they're open control. And we'll talk a little bit about the difference between open and closed loop control. That was one of the tests on the final last time, was explaining the difference between the two. I understand that almost everybody takes a course in feedback control systems right there, so you should know the difference between open and closed loop, but I'll talk about that either. Electrics tend to be cleaner than hydraulics. So far, I haven't seen a puddle of electrons on a floor, where I've seen a big puddle of hydraulic fluid on the floor. And they're the most common dry. I gave the impression that hydraulics are used a lot. Hydraulics are used in applications where you have the heavy lifting. I mean, if you're picking up an engine, you're most likely going to use a hydraulic. The moving the assembly line is most likely going to be an electric. It's going to be a relatively large electric geared down, and it's going to move relatively slow. But moving the assembly line is a slow process, and it's not a very heavy process. I mean, yeah, it takes a fair amount of torque, but it's not like picking up an engine, lifting it over, and putting it down. That requires some muscle right there. Pneumatic, these are probably the cheapest, smallest, and these are used not very often, but you'll find them in very small robots for precise work in terms of actual. They tend to be more in the end actuators that they're. Now I have seen a lot of industrial presses that use pneumatic drives that they're. So they're. I don't think they're used as much as the electrics anymore. They used to be very popular for industrial equipment. Back in the dark ages when I did factory work, we had a lot of pneumatic robots or machines. They weren't robots. They had humans. And they had to push buttons, things like that, and they would come down. And there you could hear the air press going right there. So I mean, and I've worked with a lot of industrial equipment that use pneumatic drives up there. The company I used to work for, I'll pick on this company because I was actually there a number of years. Because I worked for about 6 months before I went in the Air Force, and then when I came back, I worked for like another 3 or 4 years while I went to college half time. So, but we made brake shoes and clutch facings for General Motors and Ford and Chrysler and that's there. And this was a typical industrial factory right there. So that there, we had a lot of the pneumatic machines. Again, these weren't robots that's there. So, but remember what I said earlier, machines, industrial machines and industrial robots are not, you know, they use a lot of the same technology in terms of how things are done. Now, obviously, the robot arm is different than the industrial. When I left the industry, the robots were just starting to come out. That there. So those are the three. I think actually, as I said, I was going to do a double class, but I think I'm going to stop with that, and then we're going to get into movements. This is a natural place end a lecture right there. So 39 slides, I can talk a long time on 39 slides. That there. So that there. But when we look at the robot, that there, because today was really pretty much International Robots. We went through all the parts, and next is we're going to get into the movements. That's a completely different topic, and I just find that the human brain, getting away from the robotic stuff, it absorbs one subject fairly well, and as soon as I change gears, I'm going to confuse. You're going to not remember the second part of this, or you won't remember the first part. So I'm going to just stop with. Today's lecture is predominantly over the the major parts of the robot, right there. When we look at the major parts right here, those are our 5 major parts. Right there, the controller, the manipulator, the actuator, the end effector, and the sensors. And then I ended it with our 3 power sources, the way that there. So really we had 2 topics. So to get into the motions, it's now going to be a 3rd topic. So I think it's, regardless of my energy level, there's always a good place to just end it for the day besides. Right there. So let me, and an hour is actually